In this today's lecture, numerical is a symmetric eye section is 150 wide and 200 deep. The flange thickness and web thickness is 10 mm. This section is used for cantilever beam having a span of 3 meter and subjected to uniformly distributed load. Find the maximum uniformly distributed load that can be supported. If E modulus of elasticity is equal to 200 GPa and maximum allowable stress is 180 MPa. This is cantilever beam. Length of this cantilever beam is 3 meter. With uniformly distributed load. And our problem statement is to find this uniformly distributed load W. And section of this cantilever beam is this I section. And this I section is symmetric about x-axis axis. See, above side of this x-axis axis and below x-axis axis both are symmetric, and this I section is symmetrical about y-axis also. So while calculating moment of inertia in this numerical, we don't use parallel axis theorem. Width of this I section is 150 mm, depth 200 mm. See, thicknesses are same. Top flange thickness is 10 mm, bottom flange thickness is also 10 mm, and web thickness is also 10 mm. This section is used for cantilever beams. Span of cantilever beam 3 meters subjected to uniformly distributed load. And to find maximum uniformly distributed load, E is equal to 200 GPa. And maximum allowable stress they have given us in numerical is 180 MPa. So first write data. Width of this I section is denoted as small b is equal to 150 mm. Depth denoted as small d is equal to 200 mm. Thickness denoted as small t is 10 mm. Length of that cantilever beam is denoted as capital L and is 3 meter. E modulus of elasticity or Young's modulus is 200 GPa, gigapascal. And maximum stress sigma max is 180 MPa. We have to find W, load, uniformly distributed load acting on this cantilever beam, maximum UDL. So for this numerical, solving steps are: first calculate position of neutral axis, second calculate moment of inertia for this I section, third calculate moment of resistance with the help of Flexner formula, and after this moment of resistance, next step is calculate moment for this cantilever beam and equate moment with moment of resistance, we get this W. So step by step we solve it. First step is position of neutral axis. Denoted as Y bar. See, in this case, we don't use a1 y1 plus a2 y2 plus a3 y3 upon a1 plus a2 plus a3 formula because our section is symmetric. That means in this case simply we write 200 by 2. This depth is 200 by 2. That means from this bottom fiber to neutral axis, distance is 100 mm. So write 200 by 2. Depth is 200 divided by 2 is 100 mm position of neutral axis from bottom fiber. Why we directly use this method? Because our section is symmetric, and our previous lectures numericals, our section is not symmetric. About x-axis, about our section is not symmetric. That's why we use this formula: y bar is equal to a1 y1 plus a2 y2 plus a3 y3 upon a1 plus a2 plus a3. But in this case, directly use 200 by 2. Next, calculate moment of inertia about x-axis. In this case also moment of inertia, we don't use parallel axis theorem. We directly use BD cube by 12 formula for rectangle section and deduct these two rectangles. Because our section is symmetric. So first see, consider this whole rectangle. This full rectangle first. This full rectangle width is 150 mm. And we have to calculate moment of inertia about x-axis, about this axis. So parallel side to this x-axis is 150 mm. That means 150 as it is multiply by 200 cube divided by 12. This is moment of inertia for this yellow rectangle. So write 150 multiplied by 200 cube divided by 12. This is whole rectangle moment of inertia, but our interest is to calculate moment of inertia for this I section. So deduct these two rectangles, subtract these rectangles from this yellow rectangle. See, this sky blue color rectangles are two rectangles and their dimension is this much. That means 150 divided by 2, this much here, and minus 5. 150 divided by 2 distance is 75 mm, and 75 mm is this much distance. This much distance is 75 mm, and this web thickness is 10 mm. That means 10 divided by 2, 5 mm. This distance is 5 mm. That means 75 minus 5, 70 mm. Width of this sky blue color rectangle is 70 mm, and this rectangle is also similar, 70 mm. And depth of this sky blue color rectangle is, see, top flange thickness deduct, bottom flange thickness also deduct. 200 minus 10 minus 10, 200 minus 10 minus 10 is 180 mm. That means depth for the sky blue color rectangles are 180 mm. And about x-axis, moment of inertia of this sky blue color rectangle is similar to this x-axis side is 70 mm. That means 70 mm as it is multiply by 180 cube divided by 12. And these rectangles are two rectangles, that's why I deduct minus two rectangles multiply by moment of inertia 70 multiply by 180 cube divided by 12. So moment of inertia for that I section is 150 multiplied by 200 cube divided by 12 minus 2 into 70 into 180 cube divided by 12 is 31.96 into 10 raised to 6, and unit of moment of inertia is mm raised to 4. So 31.96 multiplied by 10 raised to 6 mm raised to 4 is moment of inertia for that I section. So erase this all. Now next, use flexural formula. Third step is using flexure formula. Flexure formula is m by I is equal to sigma by y is equal to E by R. We have this sigma in numerical. They have given us maximum stress is 180 MPa. We have this y. We calculate this y in our step 1, 100 mm. We have also this moment of inertia I. In step 2 we calculate I. So use these two. M by I is equal to sigma by y. With the help of this equation, we calculate this moment of resistance M, sigma max upon y max multiplied by I. Sigma max is 180 MPa. MPa, that means 1 MPa is equal to 1 Newton per mm square. That means this is 180 Newton per mm square. And Y max is 100 mm. Multiply by moment of inertia is 31.96 into 10 raised to 6. So moment of resistance is 180 into 31.96 into 10 raised to 6 divided by 100 is 57.528 into 10 raised to 6 Newton mm. 57.528 into 10 raised to 6 Newton mm. Why this unit is Newton mm? Why this unit is not kilonewton meter? See, this 180 this 180 unit is in Newton per mm square. This moment of inertia is in mm raised to 4, and this 100 is in mm. So see, this mm and here 4, 1 mm cancel. That means remaining 3 mm cube, and this mm square and this mm square cancel. That means remaining is mm. That's why Newton mm unit. And convert this Newton mm value into kilonewton meter. For convert 1 Newton to kilonewton, see here, 1 Newton is equal to 10 raised to minus 3 kilonewton, and 1 mm is equal to 10 raised to minus 3 meter. So multiply 10 raised to minus 6. That means this 10 raised to 6 and 10 raised to minus 6 get cancelled. 57.528 multiplied by 10 raised to 6 multiplied by 10 raised to minus 6 is 57.528 kilonewton meter. So moment of resistance in kilonewton meter is 57.528. Now next calculate moment for this cantilever beam. Bending moment. Cantilever beam bending moment is, see this W uniformly distributed load acts here center at this beam. That means at L by 2 distance from fixed end, this W load, and take moment here clockwise, this W into this W L here. This movement WL load movement at this fixed end WL into L by 2. That means bending moment is WL square by 2. Once again, see this uniformly distributed load W is in kilonewton meter. Convert this uniformly distributed load into concentrated load. That means W, this uniformly distributed load, multiply by length of this beam, and this WL acts on center of this beam, and center is at L by 2 distance from fixed end. And for bending moment, this WL load multiply by perpendicular distance L by 2, WL into L by 2, WL into L by 2. That means WL square by 2 is bending moment for cantilever beam. So bending moment for cantilever beam is WL square by 2. Now next, equating bending moment with moment of resistance for equilibrium. Moment of resistance is equal to bending moment, and moment of resistance is 57.528, and bending moment is WL square by 2, and here length of that cantilever beam is 3 meter. So here is 3 square. Therefore W is 57.528 multiplied by 2 divided by 3 square is 12.784 is uniformly distributed load. Sorry, 12 here, not 72. 12.784 kilonewton per meter. Our problem statement is to calculate uniformly distributed load for this cantilever beam with length 3 meter, and we calculate this 12.784 kilonewton per meter. For that, I cross section cantilever beam. Thank you very much.